So yeah, welcome everyone. Today's specialty talk is from Rajika Kuruwit from University of Copenhagen. And Rajika, please take it away.
Yes, hi. Thank you for giving me the opportunity to talk to you. I'm really excited. So I'm currently a postdoc at the University of Copenhagen, but I will be moving to the Heidelberg Institute for Theoretical Studies in October. I guess I will be talking about unraveling binary and multiple star formation. I wasn't quite sure what to cover, so I was trying to cover basically everything. So in the talk, I'll kind of try to blitz over the theoretical component of my PhD, but I also had an observational component, which I think you might be interested in, and then talk about some more recent work I've been doing at the University of Copenhagen. This image here is actually a cover photo that I tried to submit for a Nature paper that that was recently accepted with some of the astrochemists here. I don't think it was accepted, but it's still really nice. And I think it kind of shows the complexities of binary multiple star formation, where you have, accretion streams coming in, bridges. Can you see my mouse actually? I hope, yes. Bridges between the stars, you have outflows that kind of stir everything up. So why do we care about multiplicity? Well, this is a plot from Mo and DiStefano, who sort of compiled together many surveys of multiplicity of various stars in the main sequence. And what we see is that the x-axis is the mass of a primary star, and this is a fraction of those stars that either are single, so the red line, binary, triple, or quadruple. So if you look at the single star fraction, about 60% of stars like our sun are single stars, but this fraction decreases as you go to higher and higher masses, because it's overtaken by the binary star fraction, the triple star and quadruple star fraction. So a lot of stars exist in binaries and multiples. What we also observe when we look at star forming regions is a lot of stars. So in the class 0 phase, in the earliest phases, about 2/3 of them have companions. And so a lot of stars are born with siblings, but then this multiplicity fraction decreases as you go towards the main sequence. So that's implying that these multiple star systems, they interact and disintegrate as they move towards the main sequence. And this is really interesting to think about because, while these young stars are interacting, they host disks, which can be the site of planet formation. So you kind of want to think about the implications of binarity on possible planet formation. And in the context of our own solar system, so when you look at the D to H ratio of Oort cloud objects and Jupiter asteroids, this is the D to H ratio that we see in our solar system. And when you compare it to star formation in clustered regions and star formation in isolated, like relatively isolated star forming cores, it really looks like our own solar system was formed in a clustered region. So it might not be unlikely that our own solar system our own sun once might have had companions and it became the single star. And also when you look at planets today, we have detected, almost 5,000 exoplanets, and 700 of those have more than one sun. Those are often in configurations where the stars have a quite large separation, the planets going around one of the stars. But we've also just found about 30 circumbinary planets. So how do these planets form? When we think about planet formation, we have kind of sort of ignored binaries and multiples, partly because, thinking about a single star is easier, and also maybe there's some anthropocentric bias because we only have one star. So these planets in binaries, they do form from disks. So this is a plot from Harris et al. And this is the projected separation of binaries in Taurus, I think it was. And this is basically a proxy so the flux is basically a proxy for the mass. And what we see is that for binaries that have separations larger than 300 AU, the distribution of disk masses is basically the same as that of single stars. This is what these points are. But when you go to lower and lower separations, it looks like they get smaller, and this is probably due to tidal truncation. So maybe that could hinder planet formation because it just is small and there's less stuff there to make the planets. But what we also see is that there is this group of disks up here, which are actually the circumbinary disks, and they are comparable to the most massive disks we've seen around single stars. There's also a curious aspect about these circumbinary disks. So when we think about the lifetime of protoplanetary disks, we've derived the lifetime of disks is probably around 5 million years. So this is a plot of diffraction of stars in different clusters. And you can see in the younger clusters, it's much higher and it decreases as you go to older and older clusters. So we think like the typical protoplanetary disk lifetime is about 5 million years. But when we look at some of these circumbinary disks, we've actually found a lot of them are really old. So some examples are here. So they're much greater than 10 million years. And the question is, are these circumbinary disks an anomaly, or are they typically long-lived? And what could that mean for planet formation? So I've mentioned a lot of open questions, so I'll try to go into my work. So in my PhD, I was trying to investigate the formation of disks and binaries and how long they live. And I had two components to that. In the first component, I used simulations, so I'll try to skip ahead. So I used a code called Flash to simulate the formation of binaries from a single protostar core. So the core was 3,300 AU radius and 1 solar mass, and it was in pressure equilibrium. It was very ideal conditions to encourage the formation of a binary. I put in a density perturbation. So I will skip over the first project just because I had to cut down the size of my talk. But in my first project, I was kind of looking at the formation of a single star compared to a type binary and a wide binary, and looking at how things differed. And the main thing that we sort of find is that binaries are, their outflows are less efficient at transporting momentum and angular momentum and mass. And it kind of makes sense because a binary needs to have some angular momentum to maintain that orbit. But what we found from these simulations was actually is very curious when the stars start to get really close because the disks were kind of being destroyed and disrupted. So we wanted to investigate that further, and we added a new level of looking at turbulence. So I was looking at how we put turbulence on top of this and how turbulence could play a role in building disks. So we tested 3 different levels, Mach 0, so no turbulence, Mach 0.1 and Mach 0.2. And what that looked like is this. So on the left is a no turbulence simulation. On the right, this is Mach 0.1 and Mach 0.2. And the filament kind of forms from the density perturbation, but then the stars have their own disks, which as they start interacting, the disks are being disrupted. And this obviously could hinder planet formation. This is the very early stages though. But what you do see in most of the cases is that the material is sort of being redistributed to form a circumbinary disk. And this is this is the strongest and the most turbulent case compared to the least turbulent case. And this is sort of in line with other simulations as well of just disk formation in single stars. The turbulence can help build a much larger disk because you have that turbulent support as opposed to material just falling straight onto the stars. And a lot of simulations have sort of been showing this similar evolution, but we've never really been able to see it until last year. So this paper came out late last year, which is really cool. This is a young binary, and you see these sort of spiral arms. And this could be a binary in this stage of sort of inspiraling, and it's a circumstellar disk being redistributed into a circumbinary disk. So that's really interesting. And then, I was investigating the influence of turbulence on the disk properties. So here, this is a big plot, but basically this is just the density profiles, column density profiles, and this is the cumulative mass for the non-turbulent Mach 0.1 and Mach 0.2 simulations. And we're basically trying to see if we could measure the disk sizes. And in our simulations, the circumbinary disk was barely existent, but when you got to the Mach 0.2 one, the circumbinary disk was quite massive. So it had 0.12 solar masses and a radius of like 70 to 80 AU. So it seems like turbulence is useful for building large disks, which is great because the universe is kind of turbulent. And then we're looking at the binary evolution. So this is the separation of the simulation of the systems over time. So we can see that the T2 is the most turbulent simulation that sort of circularizes quite quickly. And that might be because of, the turbulence kind of redistributing angular momentum, the drag kind of circularizing binary quite quickly. But then on here, we have the accretive mass. And what you can kind of see is that there are these jumps in accretion that sort of line up with periastron. So this is some evidence of epicyclocreation, and this is something that I investigate later on. But I will move on to my observations. I was quite crazy, wanted to do simulations on observations. It was exciting, but took up, it was a lot of effort, but I really much enjoyed it. So I did my PhD in Australia, so that's where the accent comes from. And we have access to the southern sky. It's pretty great. So over the course of my PhD, I observed this patch of sky, and I was looking at Upper Scorpius, which has an age of about 11 million years, and Upper Centaurus Lupus, which has an age of 17 million years. And what I was looking for was I was measuring the radial velocity of young stars in these regions, but I was targeting objects that have an infrared excess. And what I was hoping to do was to see whether the fraction of the binarity of disk-bearing stars, whether that differed from the field binarity, and that would give some insight into the typical lifetime of a disk in binaries. So to sort of demonstrate this, let's just say that the field binarity of the stars that I was looking at is about 20%, so 0.2. If the observed disk-bearing stars had a multiplicity that was the same as the field, then that would kind of suggest that there isn't any significant difference between the lifetime of disks in binaries compared to single stars. But if the multiplicity of disk-bearing stars was much greater than the field, then that could suggest that maybe disks live longer around binaries than they do around single stars. Oh, yeah, so I should point out that Upper Scorpius and Upper Centaurus Lupus were chosen because they're quite old. So, when you look at the plot I was showing before, you would expect most of the disks to have been dissipated by 5 million years. So if there is any difference between the lifetime of disks around single stars and binary stars, it should be enhanced at these older ages. But yes, the other end is that the multiplicity of disk-bearing stars in these old regions is much lower than the field fraction, then that would suggest that the lifetime is lower in binaries overall. So that's what I was investigating. So I looked at stars in Upper Scorpius and Upper Centaurus. I was using members that were identified by Aaron Rizzuto, and he used proper motions and lithium abundances to determine their membership to these regions. So the red points are our stars, and the blue points are just other non-members. So that lines up quite nicely. And then we were looking for objects with an infrared excess. So this is the photospheric color you would expect. So this, we're using Ys, and anything above this, 3 sigma above this, we consider to have an infrared excess, probably caused by a disk. So an example is one of these objects. So when you go, Ys band 1 is shorter wavelengths and Ys band 4 is longer wavelengths into the IR. So when you're the shorter wavelengths, you see all the stars, but as you go to longer wavelengths, all that's left over is like the disk emission. So I observed these every year for 3 years. Sorry, yeah, a few days every month for 3 years. So I could see if there was any radial velocity variation. And I actually identified 2 spectroscopic binaries. So these are some, and you can kind of see at at 2 epochs, we could get like the 2 peaks. So that's quite nice. This one was much stronger. But yes, not all binaries are spectroscopic. So we did have to measure the RVs over a few years to see if there was, to find single line spectroscopic binaries, basically. So we did that. And then after measuring all these RVs, I had to basically do some Bayesian analysis. So after I had the radial velocities, I simulated various binaries and also single stars, so just a constant radial velocity. And I worked out a likelihood of them being a single star or binary, and then this Bayesian ratio, so the likelihood of it being a binary compared to the likelihood of it being a single star. So if this gamma was much greater than 1, then it's very likely to be a binary. If it's much lower than 1, then it's very likely to be a single star. So after more complicated Bayesian analysis, I managed to come up with a fraction. So using this Bernoulli trial. So I was kind of deep down in my heart thinking, I really want binary disks to live in binaries for longer, because that would be great for plant formation. But what did the results say? So when looking at the stars, the actual field binarity is closer to about 11%. So I was looking at FGKM stars. And from our disk-bearing stars, the binarity that we got was these two distributions. So both of them are technically like in agreement with the field binarity of the field stars 2 within 1 sigma. So this is really interesting because I guess it's kind of suggesting that there isn't any significant difference between the disk lifetime and binary stars compared to single stars. But I was only looking at FGKM stars, and my sample wasn't the biggest, but that could be the case. And we were suggesting it could be a combination of circumstellar disks being disrupted, so being tightly truncated, and they can disperse quickly, but circumbinary disks kind of living for longer because we observe a bunch of these circumbinary disks that are quite massive and quite old. So maybe it's those two factors, because when we were searching for objects with infrared excesses, we weren't distinguishing between whether they were circumstellar disks or circumbinary disks. We're just looking for infrared excesses. But that was really fun and interesting. But I will return back to the theory. So I said in here, we were seeing evidence of epicyclocreation in this, and I want to investigate this some more. So I ran these, the turbulent simulations for longer, and this is just an updated version of the plot. Sorry, there was some whiplash. I just went from observations to theory. I will continue, sorry. So this is the separation of the binaries separation. So you can kind of see they in spiral over time. And this is the accretion rate. And the accretion rate, you can kind of see it doesn't vary as much, but then once they start to really have proper orbits, the accretion rate does vary quite significantly. And the orbits also, they go from high eccentricity to low eccentricity. So they're circularizing. And I wanted to see if there was, any dependence on the binary orbit on the accretion rate. And naively, you might just try to phase fold all this over the whole binary orbit. But because they're evolving so quickly through different eccentricities, that doesn't really make most sense. So what I did was I separated these orbits into different eccentricity bins. So the eccentricity bins are here because the T2, so the more turbulent simulation inspiraled much faster. It has one less eccentricity bin, but I needed to make sure I had eccentricity bin so I had enough orbits to phase fold over and really kind of get some proper information out of this. So when I phase fold the data, so this is for the high turbulence, this is the orbital phase. So orbital phase of 0 and 1 means periastron, that's when the stars are the closest, and 0.5 is apastron, so that's when they're the furthest apart. And this is the accretion rate. And what you can see at high eccentricity, so this is eccentricity of higher than 0.7, you kind of get this really strong modulation. You get this enhancement at periastron. And you kind of also get that when you go to this eccentricity, but it gets weaker and weaker as you go to lower and lower eccentricities, and it's basically non-existent below 0.1. So that was for the high turbulence simulation. For the lower turbulence simulation, you also get this enhanced accretion near periastron, and that also does get weaker as you go to lower and lower in eccentricities. So I wanted to see whether there was any dependence of the accretion strength on eccentricity. So I defined this beta value. So beta is just a ratio of the accretion rate during the burst and the quiescent accretion rate. And what I was expecting to see was that with higher eccentricity, you would get stronger accretion. So if this one line just divides between when you actually get pulsed accretion and when you don't. So for the T2 one, you do sort of see that when you go to higher and higher accretion, you get stronger accretion rate, but then it kind of falls down over here, and I'll talk about that. But for the T2 one, that you kind of get stronger and stronger accretion up until here, but then it sits around, the burst accretion is about 3 times greater than the quiescent accretion, and doesn't grow much stronger. That was really interesting. And it could hint that maybe the strength of the accretion during this periastron passage isn't dependent on eccentricity alone, and there could be other factors involved like turbulence. What's happening in these cases, we think because the eccentricity is so high, the separation at periastron is smaller than the radius of the circumstellar disks, and from the movies you'll see that they actually get quite violently disrupted. So that's why you get a burst of accretion, but it is shut down quite quickly at these eccentricities. And I want to try and compare this with observations. So we don't have observations of long period binaries having pulsed accretion because, well, we can't observe them for very long because they have periods of decades to centuries maybe, but there is actually a handful of short period proto-binaries that we have seen this pulsed accretion. So a couple of examples is TWA3A and DQ tau. So these are solid lines, and they have periods of like a couple of weeks. So we can actually observe them over multiple periods, and we do see that they have this modulated accretion, and you have these bursts at periastron. So what and this was another simulation that they were compared to. So what I did was I picked the phase folded accretion curves in the bin that was closest to these binaries. So the binary has a eccentricity of about 0.6 or so, and compared it with the observations. I had to normalize it though, because my binaries were from very early stages. They have very high accretion, whereas these two binaries are class 2. So they have lower accretion rates, but we still want to see whether we could reproduce the shape. So our T1 simulation kind of reproduces the shape a lot better than the T2 one. So T1 is a low turbulence case. So it kind of matches the quiescent accretion rate and the peak accretion rate pretty well. The T2 one sort of is much more exaggerated. So it has a much higher accretion burst and lower accretion rate. And that could kind of make sense because older disks, I guess, would have lower turbulence. But what we don't quite get right is the timing. So in our simulations, the burst happens a bit before periastron, but from the observations, it really happens at periastron. And that could have something to do with the physics that we have in our simulations, maybe. But that would be interesting to investigate. So the next steps, you saw my simulation setup. It was very ideal, kind of, I had this spherical core, and I sort of just worked with that. But, like I said, the universe is turbulent. I did try to investigate turbulence on the core, but really, it's on much larger scales and there's a lot of feedback. So you got like these jets that kind of give mass momentum back to the ISM and stirs things up. And, stars, they also form in clustered environments, not necessarily isolated. And we have to sort of take this into account when we're really looking at star formation. And one way to do that is to, we can have this turbulent box and use this technique called the zoom-in technique. So an example is that you have a larger box that you stir up, and you can let stars form within this box. But if there is a star that you're particularly interested, you can do a zoom in. So this is one way to sort of try and capture the turbulent environment in which a star is formed, but also go down to higher resolution around where the star is forming to really understand how the star is growing, how mass is being accreted onto it, and how the jets create feedback. So this is what I've been doing, been running zoom-ins to sort of really understand the formation pathways of certain binaries. And in particular, I was using these zoom-ins to help understand these observations of a young proto-binary. So this was a binary where this purple line is a disk, and there's actually another companion down here. But this is a radial velocity curve. And usually what you would see is a strong dipole because it has a disk and one side is being redshifted, the other side is being blue shifted. But what was being observed here was that there is this sort of quadrupole structure, and that was quite curious. So Jas Jørgensen, he's the one that observed this, kind of asked me if I could help make sense of this and whether the binarity of this object was playing a role in why it was producing this quadrupole moment. So so I used my zoom-in simulations to try and make sense of this. The problem with comparing simulations with observations is that simulations, they evolve over time, but observations, they are just a snapshot in time, and that can make it quite difficult to compare. Another complication is that radial velocity is quite dependent on the observer. So what I did was I had some simulations of binary star formation from these zoom-ins. So I had one star here, and I calculated some projection vectors over which the projected separation would equal 200 AU, because the observed binary has a separation of 200 AU. So I did this for 4 different zoom-in simulations, and there's 8 different vectors. So 32 movies, essentially. An example of one of those is this. So this is the, I guess, the continuum image proxy, and this is a radial velocity. And the projection vectors are such that the binary separation is fixed. And what you see in most cases is that you do get the strong dipole moment, but actually there were certain times where you got a quadrupole. So I went through all these movies to sort of find vaguely when quadrupoles were happening, and then gave those just snapshots to the other authors, and they ranked them individually, and we compiled our best ranks. So these are our best matches. So you can kind of see in some cases you sort of have like a really global quadrupole, in other cases a bit more local, but you could get it occasionally, which is encouraging. So I said that we did this ranking by eye. I currently have a couple of master's students who are trying to use machine learning to use synthetic observations from our simulations to compare with actual observations and see if we can get the same ranking, or automate this eventually, because we're entering the age of big data and there's just so much data to go through, both observations and simulations. So they're doing some really exciting stuff, but this is what we came up with. And we wanted to see, okay, we got these times where there's a quadrupole moment. Does the binarity of the object have anything to do with getting this quadrupole moment? So what I did was I looked at various binary components, characteristics, and just saw when we were getting this quadrupole moment. So here, this is the orbit number of the binaries that I did zoom-ins of, and this is various characteristics. So this is the separation, this is the accretion rate, this is the eccentricity, and this is the disk size. And we also had one high-res simulation just to see if there was any significant, basically to see if our results had converged, and they seemed to pretty much agree. So what was really curious is that for our B1 and B3 binaries, they are lower mass. We got the quadrupole moment near apastron, which was really interesting. These binaries are also quite high eccentricity, and they have very strong sort of modulation in their accretion rate over in orbit. B2 didn't quite show that there was this one point here, but B2 is quite massive compared to what we think the mass of the observed binary is, and it was also low eccentricity. So we're not quite sure whether B2 was the best comparison with the observations, but B1 and B3, they are closer. So hopefully, yeah, what we're seeing is that the binary was producing this quadrupole moment near apastron. We think it might be because well, actually the next slide goes into investigating this. Near periastron, they have a large accretion burst which can produce outflows, and the outflows are being dragged along the orbit. But also at the same time, when you'll see from my next movie, is that there are accretion streams falling onto the stars, and those accretion streams actually follow the stars along the orbits, and they can contribute significantly to the radial velocity signature. So basically I had to go and look at what was happening. So this is the movies from the XYZ directions, and I had to really find the times and see what was going on. It's quite complicated because there are outflows that sort of feed back into the environment. There is accretion streams coming from various angles, and as I pass periastron, sometimes a little bridge exists briefly, and then that can be disrupted again. So I had to go through these and really kind of reconstruct what was happening in these cases and what was happening when we got the quadrupole moment. And what we think is sort of happening here is this schematic. It's a bit fuzzy. So this is the foreground star and this is the background star. And what we think happens is, at periastron, they have the accretion burst and the outflows are being launched, but the binary is also moving. So the binary is moving and the outflows are being dragged along the orbit. But also at the same time, these accretion streams are following the star as they go around, and they can contribute to the radial velocity signature. And this is really important because in my previous simulations where I had an isolated core, I wouldn't be able to reproduce these results because it basically the star was in an isolated environment. But with these zoom ins, we could capture this movement of mass from the larger scale environment down to the small scales. So that's very important. So that's really cool. This paper is going to come out in a couple of weeks from Nature, so keep an eye out for that. And what else have I been doing? So I have been investigating protostellar multiplicity. So using these same turbulent simulations, so we did zoom-ins on a couple of systems that formed binaries, but I've been using these simulations to hopefully gain an insight into the formation pathways of binary and multiple star systems. So this is a figure from Tobin et al. And use of protostellar young protostars. The x-axis is separation, and this is companion frequency. It's basically a measure of multiplicity. And what we see is that there is this peak at 75 AU. So there's a lot of binaries that have separations of about 75 AU. And there's also this other peak that goes out to about 3000-ish AU. And this is being observed in other star forming regions. So this is from Perseus, but it's also been found in Ophiuchus, at least the smaller peak is. And more recently in Orion, you can also sort of see this bimodal distribution, but I will focus on the 2016 paper because that's what I've been comparing my simulations to. So it's very interesting to have this bimodal distribution and what is the origins of this? So when this bimodal distribution was being found, this larger peak was kind of being attributed to core fragmentation. So core fragmentation is where you have a large cloud of mass. That's kind of what my first simulations were. You just had this core, and that core was fragmenting into individual stars. So these individual stars can have their own disks. So I think the core fragmentation happens on much larger scales of a few thousand AU. And this peak at 75 AU was sort of being attributed to maybe disk fragmentation. So in disk fragmentation, you can have a star with a very massive disk that is gravitationally unstable. And that can lead to fragmentation forming other stars. But what you saw from my PhD simulations and other simulations like the zoom-in ones, you can have stars fragmenting in a core and then they experience significant in-spiral where they fall into each other and reduce their separation and can harden. So simulations for a long time have been showing that binaries that form from core fragmentation can in-spiral to these separations of tens of AU. So I sort of wanted to investigate what is the contribution of core fragmentation on these protostellar statistics. And the way I did this, so I actually have 6 simulations, but I'm only showing one movie because my talk kept on crashing. Basically, we have a 4 parsec cube turbulent box, which we drive for 20 dynamical times, and then we let stars form, so the sync particles. And this is a 3000 solar mass box, but we also had other masses, so from 1500 solar masses up to 12,000 solar masses. So we're investigating all these different star forming environments to see if that plays a role in the formation pathways of these binaries. And we selected the simulation conditions such that we only resolve core fragmentation and not disk fragmentation. So our resolution is 50 AU and the accretion radius of our sync particles is 8 cells. So cells can't form within 400 AU of each other. I guess close to 800 AU, you have the 2 accretion radii. So that means we're only resolving core fragmentation, but our sync particle smoothing radius is down to 8 AU. So our sync particles can actually evolve to much smaller separations. So we are resolving like the whole separation range that the Tobin paper plots. So this is just, yeah. And we have periodic boundaries. So we just have our stars forming and you can kind of see if they can kind of form in this clump here and they can fly around. And the result of this is this figure, and this is very messy, but I'll walk you through it. So the x-axis is the star formation efficiency. Each simulation was run until they had 5% star formation efficiency. So this is basically time. And this is the lowest mass simulation going up to the highest mass simulation. And every one of these lines, it's hard to see, is the separation of all the bound systems that form. And the low mass simulation, we don't have as many stars. When you go to the high mass simulation, we have so many systems that it's overlapping. But the main thing is that you see systems form at larger separations and they in spiral significantly. So a lot of systems experience, significant in spiral. And you might be wondering what these markers are. So these markers are the different formation pathways that I identified. So we see many systems experience significant in spiral. But these are the formation pathways that I sort of discovered from the simulations. So the first one is core fragmentation, which we all know. So you have a core, you have a star forming, and I determined that if a second star was born and it was born bound to another star, I called this core fragmentation. Then there is the other scenario where you have a star being born. It's technically unbound, but later becomes bound to the system it was most bound to at birth. And I called this delayed core fragmentation because there was some delay between when the star was born and then when it actually became bound to its system. And the third scenario is dynamical capture. So this is when a star is born, is technically most bound to this system, but later becomes bound to another star. And that could be because it just came closer and captured it. And what you can see is that, a lot of these systems form through different pathways. So the blue boxes are bound, lots of stars being born bound through core fragmentation, but also a lot of systems being formed through dynamical capture and some through this delayed core fragmentation. So I wanted to count up the number of systems formed through these different pathways. So basically, I count up every single one of these points and see what the fractions are. And the result of that is this. This is the lowest mass simulations to the highest mass ones. And the colors are the same. So blue is bound and the red is a dynamical capture. And what we see is that above a certain density, basically about 55% of the systems that formed are through dynamical capture. And we think this is just because the stellar density is so much higher that the likelihood of capturing another star is higher. But then also in the lower density simulations, you do need to have a much larger overdensity for a star formation to be initiated. And then that means, when a core fragments in these lower density simulations, the fragments are more likely to be bound. So we try to investigate this by measuring 2-point correlation functions. A 2-point correlation just measures how clustered something is. So you measure the separations between every single point and then compare it to the uniform distribution, and typically the result is a power law like this. And the steeper the gradient, the more clustered your region that you're looking at is. So the blue is the low density simulation. This is just that snapshot star formation efficiency of 5. It's much steeper compared to the other simulations. The brown is the highest mass simulation. It's got a shallower gradient. So this is just at one time, but I measured the gradient over the entire simulation. So the blue again is the lowest mass simulation, and is the lower the number here, the more clustered it is. So the lowest mass simulations consistently more clustered over the lifetime of the simulation compared to the higher mass simulations, and this sort of makes sense. The star formation is a lot more clustered in the lower mass simulations. I also want to see if we could gain some insight into the typical fragmentation scales of these systems. So what I did was plot the initial separation of these systems. This is the X, this is the separation, sorry, and this is just a number of systems, and these are stacked histograms. So I tried to fit a Gaussian to the systems formed through core and delayed core fragmentation to see if I could gain some insight into typical fragmentation scales. And you can kind of see that maybe it moves inwards. So this is just the mean and the standard deviation of those fits. And again, maybe the fragmentation scale is smaller in denser environments, but also you could just as easily fit a straight line. So I don't know how useful this is, but I'm still investigating it. And finally, I want to eventually compare this with observations. So the problem I mentioned before, the problem with comparing simulations to observations, that simulations, they evolve over time, and observations are just a snapshot. So for example, it's very crucial what time you look at. If I look at this time, you get this valley over here. So a valley of a few hundred AU. So maybe that's what you could be seeing here. You get this there's two peaks and a valley in the middle. But if I look at this time, then this valley is filled in because systems have kind of inspiraled into this region. And that makes it quite difficult to compare with observations. So I won't play this whole movie because it's 9 minutes long, but I'll click along. This is, so the orange is the observations and the blue is from the simulations. This is all the bound systems, and I calculated the companion frequencies. And this is only bound systems, and it is projected separation. I haven't put on any cuts for observational biases like luminosity or accretion rate, but it varies quite a lot, and sometimes you do resolve this value, sometimes it's filled in, and that makes it quite difficult to compare with the observations. But I am still investigating this, and I do plan to see whether, you know, putting on some of the observational limits could resolve this value that we see in the observations. And I'll wrap, well, I've only got a few minutes left, but I'll talk about some of the stuff that I plan to do as well. So I'm still working on the comparison with the observations for the bimodal distribution, but I am moving to the Heidelberg Institute of Theoretical Studies, and I will continue looking at star formation. And one project that I am part of is the group at the University of Copenhagen had a successful Euro HPC and price proposal where we will be using Dispatch to do some crazy stuff to really resolve star formation from a protostar core down to sub-AU scales. So this framework is meant to be really fast and will allow us to accurately capture, yes, the movement of mass and momentum down to small scales. And this is this hopefully will take out a lot of the steps of having to do lots of zoom ins at different levels. There's a few things that I'd like to investigate with this, hopefully. So one thing that I am quite interested in is these eruptive events in young stars. So I was talking about this episodic accretion in binaries, and you know, there's a few outbursts called like FU Ori and EX loopy, and there's a few different theories for these. We're not quite sure what the origin of these different types of outbursts are, but one of them is tidal interaction with a companion. So I was intrigued by it and wondered whether my binaries could produce this. It's unlikely, but I still would like to see what the origin of these type of bursts are. So with our current simulations, this is the accretion histories of all the sync particles, and they all have so varied histories. So some of them have pretty constant accretion rates. Some of them have accretion rates that are shut off quite quickly. Some of them have accretion that sort of drops off slowly. Some of them kind of burst again later on, and some of them just have very wild accretion rates. So what I'd like to do is sort of look at these. I had this treasure trove of data. I'd like to look for some sync particles that might show evidence that they are experiencing an FU or XOR type outburst, and really investigate this with Dispatch to see what the origin of it is. Like, is it binarity, or is it some other environmental effect that's triggering these outbursts? But with that, I will leave you with my conclusion slides. So from the pulse accretion, we kind of saw that binaries with eccentricities above 0.2 should experience some epicyclic accretion, and we see evidence of epicyclic accretion all over star forming regions with like shifted snow lines. You really need to take into account the star forming environment to understand how stars grow and evolve. Isolated, they're usually not quite isolated. So you do have to take into account that they are embedded in this environment where there is lots of feedback and accretion streams. And then finally, yeah, core fragmentation can account for a large fraction of tightly bound, so binaries of tens of AU, indicating, yeah, so that peak at 75 AU might not solely be due to disfragmentation. Disfragmentation does happen, but also binaries that form from core fragmentation experience significant orbital evolution, and that probably is creating, well, you would see this in young star forming regions. So with that, I'll wrap it up there. I'm a little ahead. Thanks.
Thanks, Rajika, for a great talk. So yeah, if there is any question, feel free to mute yourself and ask question to Rajika. Michael, go ahead.
I can't hear you, Michael. You're still muted.
Yeah. Thanks for the excellent talk. So I was wondering a bit about your investigation of the formation of circumbinary disks with different levels of turbulence. So the first thing I was wondering about is the turbulence set for the initial cloud, or is this turbulence within the disks around the individual objects. And then I was also wondering, do you have an intuitive explanation for why you see the effect that you do? Is it just a matter of the amount of angular momentum in the gas?
Yeah, so the turbulence isn't driven, it's just put in the initial velocity field. So I guess that just an injection of energy, I guess, because you have the turbulent energy, and that can hang around for longer while the star is collapsing. So I think that the reason why we get the larger disk is just because you have that injection of turbulent energy in the beginning. But yeah, it can probably still disappear through the outflows and such. But you know, the simulation that I had were in the very, very early stages, like the first 5,000 years. So it might not have been long enough for the turbulence to really dissipate.
Thanks.
It's okay.
Any other question?
Something in the chat. Yes, I will do that.
Okay, yeah.
It's okay, it is a Monday morning.
Okay, so yeah, if not, let's thank Rajika again. Rajika, thank you for joining us
Yeah.
today, and yeah, hopefully you'll have a chance to visit here in person and enjoy the pizza lunch.
Yes, that would be great. Thank you again for giving me this opportunity.
Okay, great, thank you.
Bye.